because, like, at the end of class or something like that, or send me an email if you remember on the weekends, because maybe I'm not going to change it by then because my memory is good. Okay, listen up. So what I want to do is I want to take a class, and I just want to, Jonas, that was really good. You were able to type while staring at me.
Sorry.
That was pretty good. I can definitely not do that. Yeah, there's no keys, there's no like tactile. I think so, only because there's like real buttons on here. With a cell phone, I don't know if I could do that. Do you know what I mean?
Use voice.
Yeah, you can use voice text.
Yeah. Touch screen.
Yeah. No, but there's no buttons to figure out where the hell your thumb is. Okay. We have kind of, we've kind of gone over 3 different ways to be able to answer enthalpy problems. Almost. You can think of it in a few different ways. There's traditional unit analysis, and that's what we did on that 11.1, 11.2 quiz. Then there was Hess's law, that was our 11.3 notes, and then there was enthalpies of formation. Now what I want to do is I want to go over a few questions, and I want to try and identify, okay, when would we use unit analysis, when would we use Hess's law, and when would we use heats of formation? Because there's a bunch of different questions, and they could all ask, what is the molar enthalpy of something? But there's radically different ways of going about that process. So what I want you to think about here is that energy problems can basically be stripped down into like 3 types of problems, okay? So calorimetry, or any temperature change at all. If there's a temperature change of a substance, what I want to ask you is, what thing should be the first thing that pops into your mind?
Unit analysis?
Yeah, we're going to be using unit analysis. And in order for us to use the unit analysis, Jordy,
The SHC.
yeah, that specific heat capacity is probably going capacity. Wasn't there something you screwed up on a couple weeks ago?
No, I don't.
I totally forgot what it was.
You got the wrong guy.
Yeah, right. So we're in order for something to change its temperature, you need to know how much energy was added to that substance, or how much energy was taken away, and then you also need to know what the specific heat capacity of it was, because the specific heat capacity will tell you, oh, well, if this much energy was changed, then this is the temperature that will be resulting from that. If you see a question that lists multiple reactions in a row, and it says, what is the overall reaction? We're probably going to have to use Hess's law. And I'm still unsure whether or not that's where the apostrophe should go. I mean, I know it should go there, but whether or not there should be an S afterwards. No?
Possessive.
It's possessive?
The law is the other one.
But so is that because this is a proper noun, some dude's last name? Yeah.
It's because there's an S at the end.
Yeah.
Wait.
Whatever. That's too complicated for me. No. Okay. Now, I want to be very clear. When we're using Hess's law, there are modifications on these questions that we could add that would force us to use unit analysis. So we could use Hess's law first, but then we might have to use unit analysis afterwards. Remember, we're usually typically going to use unit analysis anytime it's talking about calorimetry. And then if you get a question and it says, what's the molar enthalpy of this reaction? And it literally doesn't give you anything other than the reaction. Yeah, you're going to be using heats of formation, absolutely. So this is going to be, enthalpies of formation. Now, just as an aside, just as like if we were to take a step back from the enthalpy boot camp thing that we're doing right now. I want to bring your attention towards the board. We don't normally go over here, and that's totally fine. Did I screw it up? Yeah, I totally did. I'm not going to fix that. So this is a potential energy diagram, apparently. And when we're looking at our potential energy diagrams, here, let's put that screw up on YouTube. Perfect. So for our potential energy diagram, we're going to be looking at the heat of formation of sulfur dioxide. And somebody just double check for me, make sure I didn't bone this up. That's negative 296.8. 296.8. Good. Okay, perfect.
Yes.
Yes. Okay. Now what I want to ask you, is this the appropriate molar enthalpy of formation for sulfur trioxide? Good. This is the vapor, right? This is the gaseous version of sulfur trioxide. And so is it negative 395.7 kilojoules per mole? Okay, perfect. Now what I want to know is, remember, the enthalpy of formation. When we're talking about the enthalpy of formation, what is this substance always being compared to? What is the energy always being compared to?
The elements.
Ooh, the elements that make up that thing, right? Okay. So if we were to take this, first of all, does sulfur dioxide have less or more potential energy compared to its elements?
Less.
Why less? Because it's negative, because when we made this thing, we lost the potential energy, right? So should my reactants or should my products be higher? My reactants should be higher, my products should be lower. Perfect, good. Okay, perfect. So this is, we're going to take sulfur and we're going to add it to an O2, and I think we should actually say an eighth of a sulfur, but that's fine. So sulfur, and we're going to add it to an O2, and that's going to give us SO2 gas. And what is this enthalpy change? What's the difference in energy between here and here? Oh, 296.8 kilojoules per 1 mole. Or I guess kilojoules just because it's a reaction. Now what I want to know, so let's compare this substance and this substance. Who's going to be lower? The sulfur trioxide is going to be lower, right? So when I take my sulfur and I'm going to take 3/2 of an O2, and I have my SO3, good. This is all very holistic, okay? So which one of these has kind of, you can think of it as like a lower potential energy, the sulfur di or the sulfur trioxide? The sulfur trioxide. So what I want to know is which one of these has more energy to lose? Does the sulfur trioxide have more energy to lose, or does the sulfur dioxide have more energy to lose? The sulfur dioxide has more energy to lose. You can make an analogy to gravitational potential energy. If I stuck my pen up on a really high shelf versus on a shelf that was barely higher than the floor, which one has more energy to lose? The one high up on the shelf. So now what I want to say is that we can draw very vague conclusions about which one of these is more thermally stable. What I mean by that is which one of these is a more stable molecule typically has to do with which one has less energy to lose. Which one of these do you think is going to be more stable? The sulfur trioxide. This one has less energy to lose. And so there are less conditions under which it would be broken up. I just wanted to bring that up. I haven't seen a question like that on the diploma exam for a really long time, but basically it amounts to which one of these compounds is more thermally stable, and you have to look for the one that has the lowest potential energy. That's all. The less potential energy you have, then the more thermally stable you are, because the less energy you have to lose. Is that kind of make sense? Good. Okay, so we didn't talk about that yesterday, but I just wanted to make sure that we covered it. Perfect. Some reminders when we're doing enthalpy problems. Anytime you read something about heating up water, what are you going to be using?
4.19.
Okay, there are two ways that we can write this 4.19. We can say 4.19 joules per gram degree Celsius. And I'm going to start writing gram of water just to be very explicit that that's the mass of water we care about. What's the other way I can write this? Ooh. Kilojoules per gram of water degree Celsius. Oh, okay. You can't just change like joules into kilojoules, can you? You have, if you're going to change joules into kilojoules, you have to change grams into kilograms. Okay, perfect, so that's fine. And then we can obviously flip that whatever we want when we're doing unit analysis. If you're given a potential energy graph, remember the enthalpy is always the difference between the products and the reactants. So like we were talking about there, if I had my potential energy, and let's say I had A plus B gives us C plus D, then our enthalpy is obviously just the difference between the two. So just take those energies and subtract them. And one thing I always want you to keep in mind when we're doing this is the ratio between the enthalpy and the coefficient of the substance in question. And so I'm going to write just a very general chemical reaction. Let's say the enthalpy for this reaction was positive 300 kilojoules. What's the molar enthalpy of this reaction from B's perspective? What's the molar enthalpy of B here?
1,000. Oh, yeah.
Right? If we're looking for a molar enthalpy, that's kilojoules per mole. And so from B's perspective, if we're looking from B's perspective, it's 300 divided by 3 moles. So it's going to be 100 kilojoules per 1 mole. What's it going to be from D's perspective? Is it going to be higher or lower? Lower. It's going to be lower. So from D's perspective, what's it going to be? 75. Just keep that in mind, because that's a really easy bit of information to gather, and it will help you out tremendously when we're doing these unit analysis problems. So let's take a look at the first example, and all I want you to do is I want you to try and think about, are we going to use unit analysis, Hess's law, or are we going to use heats of formation to do this, or enthalpies of formation? Don't say it out loud. Yep.
Honey. I thought he called you honey.
No, thank goodness no, Jordy does not call me honey.
No.
So can you tell immediately what style of answer we're going to have to use? Yeah, what are we going to have to use? Unit analysis, right? And why? Why are we going to have to use unit analysis, Mark? Oh, I thought you said something. Preston, was it you that said it?
Temperature change.
Yeah, the temperature change. I thought I heard you say the C word. Calorimetry. There we go. That's a 4-letter word in my house. That's fine. So yes, because we're talking about calorimetry, that means that we're going to have to use unit analysis. Okay? Now, I'm not asking you to actually answer this question. I'm not asking you to actually... No, I know. I'm not asking you to actually answer. I'm just asking you, let's go over all the different ways that we could answer this question. Okay? Really quickly, what's your gut feeling? How are we going to answer this question? Hess law.
We're going through them all.
Hess's law.
I'm gonna stop talking.
Are we good?
Yes.
Hess's law. Good.
Yes.
Hess law. Perfect. English teachers be damned. Okay. Let's look at this one. Yeah, let's do long division. Okay, what are your three options for answering this question? Unit analysis, Hess's law, enthalpies of formation. Jonas, which one do you think it's going to be? Okay. Okay, well, maybe let's actually read the question. I'm going to give you 30 seconds to read the question. Stay silent. Nope, stay silent the whole time. Nope. George, yeah. Keep him in line. Alicia, do you want to let me know? Just in 20 seconds.
10 seconds.
Count fast. Whenever I say 20 seconds, I'm not actually counting. It's very holistic. Okay, Alicia, I think that was an appropriate amount of time. What do you want to use in order to answer this question? Hess's law. So are there multiple different equations that we can add up these chemical reactions? What are you thinking? Yep. Okay, so I totally agree. I see two different enthalpies here, but do we know what reactions they belong to? Because every enthalpy belongs to a specific reaction. You totally do know what reactions these belong to, right? So you could make them, but I don't want you to. What is this? This is the enthalpy of what? Of formation.
Enthalpy of formation.
So what it's saying, so what this question is asking you is, let's try and look this up. Do you know the enthalpy of formation of P4S3? Yes, because it tells you right here, right? So you know what the enthalpy of formation of P4S3 is? Yeah, Alicia. Yeah, that weird equation, right? Do you know what that weird equation is? Do you remember what it is?
Sigma delta.
Sigma. Is it that's the ligma. Now I know I'm not supposed to say that. I don't know what that means, but that's fine. Yeah, that's fine. Whatever.
Just ask what it is.
I can ask what it is. That's right. Oh yeah. Okay, so let's take. Remember, the enthalpy of the reaction is what? Tell me what I'm supposed to write down. Sigma. Yeah, the sum.
And triangle.
It's like kindergarten.
Wow.
Yeah. Thank you. So it's the sum of all of the moles times the molar enthalpy of formations of the products minus the sum of the moles times the molar. I have to do this backwards every single time. And I gave myself way too much room. That's fine. It's the reactants, the molar enthalpy of formations of the reactants. Yeah, but we all know what this actually means, right? Just it's the sum of all of the products minus the sum of all of the reactants, and that's totally fine. So we could totally do this. That would be totally fine, but I don't want you to right now. I just want to move on. We know how to answer it, and that's what I care about. let's take a look at this question. Take 30 seconds to read it. Try and figure out, are we going to use unit analysis? Are we going to use Hess's law? Or are we going to use enthalpies of formation? Is it talking about calorimetry? Is it talking about a temperature change of a thing? No. So for the most, like straight off the bat, probably we're not going to use unit analysis. Okay? Now, are there multiple equations for us, multiple reactions for us to add up and subtract and all that junk? No. So what's left? Enthalpies of formation. Do you see how little information you're given? It's assuming that you can look up the enthalpy of formation of all of these things. Now, remember, there's only 3 of these in the data booklet. Right? Yeah. What's the enthalpy of formation of oxygen? 0. So whatever. Yeah. Okay. Next question. I want you to ask yourself, are we using unit analysis? Are we using Hess's law? Or are we using molar enthalpies of formation? Oh.
Sour gas.
Sour gas.
Sour gas.
Well, sour gas kills you.
I was gonna say, would it put you to sleep? Permanently.
There's a whole. If you ever want to go work in anything oil and gas related, you have to take a course. It used to be called H2S Alive. So you had to be certified in this course because H2S is often found in places where you find natural gas or where you find petroleum products.
I don't know theory.
Yes. Yeah. Okay. We'll see what it's asking us for. Okay. Okay. Let's see. I don't know how brave you are right now, but I would like to see a show of hands. So put up your hands if you think it's unit analysis that we're supposed to use.
I'm scared.
Yeah, be brave. Yeah, totally. I don't know. Okay, the hands are going up and going down all the time, whatever. Okay, that's good. Thank you. Thank you for being courageous. Now, hands up if you think we have to use Hess's law. Okay, yeah, there's not multiple equations, so that one's bunk, that's moot. Okay. What about enthalpies of formation? Okay, let's think about this for a second. This is one of those questions where is it giving us a ton of information here? It's not really giving a ton of information, okay? So that makes me want to think enthalpy of formation. But usually, enthalpy of formation, we add up all the products, subtract all the reactants, and we usually end up getting the enthalpy, right? But we're already given the enthalpy of this reaction. So let's see. Is it asking us for an enthalpy of formation of one of these things? No, it's not. So we can't use enthalpy of formation here. What did I say? One of the reminders I asked you about was always keep in mind the ratio of the enthalpy and the coefficient of the substance, because that gives you the molar enthalpy of the reaction for that substance, right? So when we look at this, there we go. What's this asking? The enthalpy change for 1 mole of H2S. Do we have the enthalpy change for 1 mole of H2S? No, we have it for 8 moles of H2S. So what's the only thing, what's literally the only thing you have to do to answer this question? Take that and divide it by 8.
So it was unit analysis.
It is unit analysis. There you go. So all of those brave individuals that put their hands up at the beginning, I appreciate you. I mean, I appreciate everybody, but whatever.
Appreciate me, Mr. Wilson.
Yes, especially you.
Perfect.
Yeah. Okay. Last question. Take a look at it. Take a look at it. And let's try and see how could we answer this question.
There's 2.
Got it.
You got to actually read the question and figure out what it's asking you about, right?
I got it. Don't worry about this. Wilson, I got
Check
it.
out the diploma. It's just like
Just wing it on every
don't
question.
study.
Create a
gut
picture.
feeling.
Yeah, and you can quote me on that. That's right.
98% of the time, you have.
Yeah.
Hey, you have 25% chance to get it right.
Yeah. Oh, that makes me so nervous that you said that. Okay. Let's take a look at it. Shh. Let's read it together. Let me ask you, in a chemistry test, not a biology test, in a chemistry test, what's the first thing you should read? The actual question. When an you could, there's nothing really inherently wrong with that, right? When an enthalpy change of 200 kilojoules is observed, in which reaction? Reaction number 1 or 2?
2.
In reaction number 2. So let's think about this. In this reaction, 508 kilojoules are released, and what substance is it asking us to talk about?
CO2.
CO2. So 508 kilojoules is released for every 2 moles of carbon dioxide, right? Well, it's asking us about a mass. So you have kilojoules per 2 moles, and you want mass. How could you get mass out of this? Molar mass, right? So we're going to have to use unit analysis on this question. I understand there's multiple questions here, but it's not asking you to add them up and turn it into something else. It's just saying it's asking for a mass of this product, and it gives you the amount of enthalpy, and so you're going to have to use unit analysis. Can we do this last question? I want to give you like 5 minutes to try this last question out.
And we're just gonna have a party, right?
Yeah, and then we're just going to have a party.
Perfect.
Yeah, that's all we're going to do for the rest of the class. Because we deserve a break, right?
Yeah. Absolutely.
Yeah.
Party with Lauer.
Yeah. Party with the principal in the room. Yeah.
Dance party.
Yeah, that's right. We were very courageous this morning.
With only Michael Jackson music.
Good.
What?
Only Michael Jackson music.
Only Michael Jackson music.
Or Elvis.
Or Elvis?
Yeah, it's gotta be 2.
That's a diverse crowd of music.
Exactly. You gotta like switch it up, you know?
Okay, actually do this, please.
Yes.
Yeah.
Are you starstruck?
He's here to assess me. Oh, okay. He's here to see whether or not I'm a good teacher or a bad teacher.
And if he gets to come next year, you should have watched it. He gets to stay.
Boston, sit down. You have questions. You should be able to try this all by yourself. It's okay. Don't worry.
Wait, and it's looking for the change. So we're looking for grams. Okay, cancel moles.
You guys can-
Why would it be too low? It's a when yeah, but you want to start with
Yeah, no, I agree.
or wait. That one time what turn is this right here, right? Like you're gonna get this guy because what we did is we divided this fraction by Leonardo wants sure. Yeah, we're gonna go with one. Yes, that makes more sense. That makes more logical sense to me.
Actually, no, it's 50 for the back time.
You can't get it enough. Sometimes I don't find your way.
I don't care.
Wait, we need to get, oh wait, no, we need to get rid of
That's not right.
Grab me a bag. Did you do that bag? Yes.
Oh, what happened to him? Oh, man. Yeah, I think so. Please don't be facetious. We've never made purple drink in the class before.
Purple drink.
Yeah, I ain't ready either.
Okay. Yep. You just wanted to see if it's right? Okay, we're gonna get there. Okay, we're looking for mass in grams of carbon dioxide. What's our chant? What's our mantra? Do I have to turn off the lights? Somebody just yelled at the top of their lungs, do what you want! No. What is the molar mass of carbon dioxide? 44.01 grams per 1 mole. Okay, shh. Right? You start with what you want, correct? Yes. You want mass. What's the only other unit you got to cancel out? Moles. Do you know how many moles? Yeah, you know that for every 2 moles.
I was right.
For every 2 moles, how much energy is released? 508.6 kilojoules. Now, are we releasing 508.6 kilojoules? No. How much are we releasing? We're releasing 200 kilojoules. Kilojoules, moles, grams are left over. So you tell me how many grams. Okay. You have, please, just calm down. I'm trying. It'll be okay. This is exciting stuff. You have 20 minutes. You can finish the stuff we were working on yesterday. There was an assignment I gave you yesterday.